Good morning dear students, welcome back. I am your physics professor Dr. Nagaraj explaining quantum computation for VTU students. It is part of engineering physics syllabus. So in my previous video, that was in previous video number 5, I was talking about tensor products and how to express multiple qubits. So there I mentioned one more notation, that is called bra-ket notation. Ket notation, bra-ket notation, both put together are called dirac notations. So let me revise it little bit and then I go ahead. See, ket notation, we already familiar, is represented by column vector. It is 1 0 or ket 1 is equal to 0 1. So we already studied this. So bra-ket means just this symbol is there, you have to put it on the other side, means this way we have to put, and 0 is now called as bra-ket 0. This is called ket 0, this is called bra-ket 0. And now how to write this? Same 1 0 column vector, you write it as 1 0 row vector. And next one, this is bra-ket 1, like ket 1 we have bra-ket 1, it is nothing but 0 and 1. Okay, so these are together called as dirac notations. And in dirac notations there are some properties, like for example A is a ket vector, B is also a ket vector. When I add these two, I get another ket vector. I think I mentioned this in my previous video. Plus B plus C, that will be equal to, okay, whether you add these two first and then next, or these two first next, that is ket A plus of B ket plus C ket. So this way also we can write. This is nothing but one of the property of this is called associative property, and this can be written as A plus B is equal to C, which is equal to B plus A, that is commutative property. So like this we have some properties in the dirac notations. Of course it is not that important from the point of examination. So 99% questions will not be appearing on properties of dirac notations. Only thing is you must know the difference between ket notation and bra-ket notation. Okay, so let me go one step further. See, U is a vector. U is a vector. So it is having, okay, of course here when I say vector, it is a member of vector space. It is a member of vector space, right? So like 0 is a vector, 1 is a vector. So this is one state, this is one other state, like that. So I have one element like this. If I write this as ket, then it will be having x1, y1, right? Two elements. I already told you there can be any number of elements, any dimension, but I need only two because I want only one state, two state, that is up state or down state, or 0 state or 1 state, or spin up, spin down, ground state, upper state, like the only two states I want, that's all. That's why I take only two elements. Okay, so now you ket is x1, y1. I want to write the bra-ket of this one. What is the relation between bra-ket and ket? Remember, bra-ket of this is equal to complex conjugate of this and then transpose of this. This both put together is called Hermitian. So now I am using some different words. I am using three words here. Number one, complex conjugate, next to transpose, next Hermitian. Okay, so now what is this transpose, Hermitian, complex conjugate? One by one I will explain. Before that I repeat, bra-ket of a vector is equal to complex conjugate of ket and its transpose. Complex conjugate of ket and its transpose. Complex conjugate of any vector, and then if you take the transpose, it will generate a new matrix called Hermitian. Okay, so let me elaborate with the example. I take one example and then I come back to this once again later on. Okay, so let me take one example. Let us say A is a vector. A is a vector that is equal to having some element x1, y1, x2, y2, some members, general. Then its complex conjugate, see, some of them may be complex numbers. In complex conjugate, what we have to write? Take the positive. If it is positive, negative you take negative. If you take positive, if it is negative you take positive. Like x1, it must be x1 star, y1 y1 star. Similarly x2 x2 star, y1 y2 y2 star. This is complex conjugate. Now transpose this. What do you mean by transpose? Row becomes column, column becomes row. See here, row is x1 y1, it becomes x1 star y1 star. x2 y2 becomes x2 star y2 star. So this is nothing but transpose of complex conjugate of A. So A complex conjugate transpose, that is nothing but Hermitian matrix. That Hermitian matrix we represent like this. This we have to pronounce as dagger. So A dagger is equal to transpose of complex conjugate. Let me take one example and then I explain this once again. Let us say there is one matrix having elements like this: 1, 2i, minus I, 0. So these are the 4 members. Then its complex conjugate becomes 1 as it is, 2i becomes minus 2i. That's what I told you. If there is plus I, you take minus I. If there is minus I, you take plus I. Like that. So minus I is there, I take plus I. Then 0 as it is. Sir, if there is no complex number in the given matrix, what to do? Don't worry. See, like this. This is not a complex number. I retained as it is. 0 is not a complex number. I retained as it is. So only if there is complex number, you have to interchange. So for example, if this is 1 plus 2i, what to do? Don't worry, if it is 1 plus 2i, you write 1 minus 2i, that's all. Only thing you have to change I to minus I wherever it is. So that's all. Let me continue with this. So this is minus 2i. Okay, now comes transpose. Transpose means A star T, that is equal to row becomes column, I said. So 1 minus 2i is the first column, I and then 0 is the second column. Okay, so now I can say this is Hermitian of this. Okay, so this is our original vector and this is a transpose of complex. Now this and this are now Hermitian. So this is the Hermitian of this. Okay, I can write this as A dagger. Got it? So that way, coming back to this, complex conjugate and then transpose of the ket gives you what? Gives you bra-ket vector. Okay, like this. These are all operations. We call them as operators. See, when I come to operate, I will come back to this. I solve numericals also. Just I am giving the definition. What do you mean by Hermitian? Hermitian, this is also called as Hermitian operator. What is Hermitian operator? It is a transpose of complex conjugate of given matrix. So given matrix was in this form, I 2i minus I 0. So by the time I come here, it becomes complex conjugate. So complex conjugate is also an operation. So what operation I did? I changed it to minus I changed it to I. Next step, again one more operation. A star became A star transpose. In the transpose, row becomes column, column becomes row. Okay, so when you do 2 operations on the matrix, you are going to get this. This is nothing but Hermitian. Okay, see, in this chapter we are going to use these terminologies, operations. What is operation? Basic question. In mathematics, and by now you already know what is an operation. In mathematics, operation means it is a process. It is a process which takes a given function into some other form, given number into some other number. Okay, given equation into some other equation. For example, square root is an operation. Square root is an operation. Suppose when it operates on a number, let us say it operates on 4. What you are going to get? You will not get 4, you will get 2. That means square root of 4 is 2. So square root is an operation. I hope you got it. Okay, similarly, differentiation, d by dx, this is also an operation. What this operation is? Sir, it is nothing but differentiation, sir. So suppose if it operates on, say for example, some number, it operates on some number, say 2. What you are going to get? 0. That means 2 converts into 0. Why? Because we all know differentiation of a constant is 0. Suppose if it operates on say sin x, differentiation of sin x is cos x. Definitely when the number or the function or the equation is operated by something, same operation, same number you are not at all going to get. You will get some other number, some other equation, some other form. See, when I operated root on 4, I got 2. When I operated d by dx on 2, I got 0. When I operate d by dx on sin x, I get cos x. Similarly, when I operate integration, this is also an operation. If I operate on sin x dx, I get what? Minus x plus c. Okay, these are all fundamentals. So, these things are called operations. Did you follow, my dear students? Okay, I hope you followed. What I said here, when some operator operates on a number, same number will not be there. Same function will not be there, same equation will not be there. Okay, suppose if A is the operator, whatever may be the operator, it may be square root operation, it may be integration operation, it may be division, it may be multiplication, it may be cube root, any operation, summation, yaud ಬೇಕಾದರೂ ಆಗಿರಬಹುದು. When it operates on some vector, say ket A, then ket A converts into ket B. So it takes the number or the vector into some other form. This is what I said. Okay, suppose if this operator maintains the same number, same matrix, same state even after the operation also, like even after differentiating sin x, if I get sin x, actually it is not possible, by chance if I get sin x, or even after integration of sin x, if I get sin x, by chance, 100% it is not possible. By chance, if square root of 4 is going to be 4 only, by chance, I am stressing this word by chance. Of course, in science there is no chance, in mathematics there is no chance, mathematics is perfect. Square root of 4 never gives you 4. Did you understand? Therefore, square root or d by dx or integration, they all will not certainly retain the number as it is. But please follow. There is one operation, it will keep the number as it is, keep the equation as it is, keep the term as it is. Do you know what it is? It is nothing but multiplication of that number, multiplication of the trigonometric term, multiplication of that equation by 1. Yes, it is by 1. What I mean to say, if I multiply 4 by 1, yes, I get 4 only. If I multiply sin x by 1, I get sin x only. Understood? So this one multiplication by 1, addition of 1 certainly not. 4 plus 1 is not 4. 4 into 1 is 4. Multiplication by 1 is going to retain the number as it is, function as it is, equation as it is. So this I call as identity operator. What do you mean by identity operator? Identity operator retains the number as it is. This is in our general term. 1 is identity operator. Same way, even in matrix also, even in quantum computation also, we have identity operator. That identity operator keeps 0th state as it is, 1 state as it is, 0 state as it is, 0 1 state as it is. Whenever that identity operator operates on any state, whether it is a basis state or state vector, multiple qubit or single qubit, yaudra meladru act madli, the same state is retained. Like 1 into 4 is 4, 1 into 100 is 100, 1 divided by 100 is not 100, 1 into 100 is 100, 1 plus 100 is not 100. Means multiplication by 1, that is identity. Similarly, here also we have identity operator. It is represented by I. If it operates on ket 0, you get ket 0 only. If it operates on ket 1, you get ket 1 only. If it operates on a vector ket A, it get A only. So I is identity operator, and in matrix form it is given by 1 0 0 1. So dear students, in this chapter we need solid background, we need fundamentals of matrix. Of course, it is a square matrix, dimension 2 by 2. You know what is the order of the matrix? 2 into 2 means 2 row and 2 column, 2 row and 2 column. Identity matrix is like this. Now let us check this, whether when I operates on 0, whether we get 0 only. That means when I multiply 1 0, whether I get 1 0 only or not. I check this. Dear students, I am checking this. So I means 1 0 0 1, correct? And ket 0 means 1 0. So after multiplication I must get 1 0 only. Please apply your knowledge, fundamental knowledge, how to multiply rows and columns. This into this, next this into this. This into this gives you first element. Well, 1 into 1 1 plus 0 into 0 0. First is 1 plus 0. Next 0 into 1 0 plus 1 into 0 0. So that is 0 0. So I am going to get 1 plus 0 1, 0 plus 0 0. See what I am getting? When I operate I on ket 0, I get ket 0 only, means 1 0 only, correct? You can check the next one also. Well, the next one I am checking, this one I am checking, not this one. This is general form. I check this, that is 1 0 0 1. You can pause this video and you can verify this, into 0 and 1. Well, I write 1 into 0 0 plus 0 into 1 0. Next element 0 plus 0, 0 into 0 0, 1 into 1 1. Look at this, finally it is going to become 0 plus 0, 0 plus 1. So I generate 0 and 1. Got it now? So this is nothing but identity operator. So you know what is identity operator and how to write complex conjugate. Let me give one more example for complex conjugate and then Hermitian. Hermitian is nothing but complex conjugate transfers. Let us take one more vector, vector A, that is equal to 1 plus I 0 minus I 2I. Okay, so there are three complex numbers here. Then straight away I write complex conjugate and then transpose. Complex conjugate and transpose. That means this becomes 1 minus I and this becomes plus I. It will come here because I am changing the rows into column. Next this is 0 only. This becomes 2I, that is minus 2I. Okay. So this row, this column became row, plus became minus, minus became plus. This column became row, 0 0 as it is, 2I becomes minus 2I. So this is nothing but Hermitian of A. So this is nothing but A dagger. Got it? So this way we can write the Hermitian of any given vector or any given matrix. This way we can write the complex conjugate of any matrix. So I explained you what is the relation between ket and bra-ket. Actually it started from here. Bra-ket is nothing but Hermitian of ket anta helde. Hermitian means what? Hermitian is complex conjugate transpose. Complex conjugate means what? Complex conjugate means if there is any imaginary term, means complex number, just change the sign. If it is plus I, you make it minus I. If it is minus I, you make it plus I. So here is an example. 1 2I, I wrote it as minus 2I. Minus I 0, I write it as I 0. So this is A star, that is nothing but complex conjugate. Next, what is transpose? Transpose andre enu? Just row becoming column, column becoming row is nothing but transpose. Okay, so this is a transpose. So for that I gave several examples. So there one example, here one example. In between I spoke about operator. So this is operator. It is a square root operator. This is operator. This is nothing but differentiation operator. This is integration operator. Actually in operator what happens, you know, whenever operator operates on a number or operates on a function, that function is going to change, that number is going to change, the term is going to change. But there is one operator, it will not change the number at all. That operator is called as unit, as an identity operator. That is 1 into. So when you multiply the number by 1, it is going to be the same. So it is I, identity means I. So you have to represent it as I. So that's what I have written here. This identity operator in matrix form is given like this. I is equal to 1 0 0 1. When identity operator operates on 0 ket, you get generate 0 only. When operates on ket 1, it generates ket only. So ket 1 only. So that I have explained through the example. Now the question is, sir, what is the use of bra-ket? So you have said ket is representing the state of the vector. What is the use of bra-ket? I will explain it now. Dear students, remember we are talking about quantum computation. In quantum computation, we are manipulating or making use of the states of electron, either spin up or spin down. And you know the essence of quantum mechanics, probability of finding the particle. It is one of the essence. Probability of finding electron in spin up state or spin down state or any one between the two, all are represented by what is called probability amplitude. For example, if electron always in spin up state, that means ket 1 is 100%. Always in spin down state, ket 0 is 100%. But it can be in between any two also, 0 and 1 also. That we already called a superposed state, and we know that superposed state ket psi is equal to alpha ket 0 plus beta ket 1. Keep this equation in mind. This is going to be very useful for us. Now, what is alpha and beta? Dear students, I am explaining the necessity of this bra-ket. What is the necessity of bra-ket? I will tell you the answer after I give the explanation. Okay. Alpha and beta are the probability amplitudes. Okay. Now, I already explained you how to write ket 0 and bra-ket 0, ket 1 and bra-ket 1. Now, do one thing. Operate this equation with the help of ket 1. That means multiply this whole thing by ket 1. Sorry, not ket 1, bra-ket 1. I am talking about the necessity, importance of bra-ket vectors. Ket vectors ಏನಕ್ಕೆ ಬೇಕು? State ಅನ್ನು represent ಮಾಡಲಿಕ್ಕೆ ಬೇಕು. Why do we need ket vector? To represent the state, spin up, spin down, in between, all those things. Bra-ket vector ಏನಕ್ಕೆ ಬೇಕು? Bra-ket vector ಇಂದ ಉಪಯೋಗ ಏನು ನಮಗೆ? What is the use? Is it just to confuse us? No, definitely not. There is a very important and a very useful application of this bra-ket. What is that? I tell you. So I asked you to multiply this. Well, ket 1. Oh, sorry, it's not ket 1. It is bra-ket 1 operating on psi is equal to bra-ket 1 alpha ket 0. It is operating on this, means multiplication, plus ket 1 beta 1, sorry, again and again I am calling it as ket. It is actually bra-ket, sorry. So whenever I write this symbol this side, it is bra-ket, that side it is ket. Okay, so now let me proceed further. Bra-ket 1 psi is equal to alpha into bra-ket 1 ket 0 plus beta into bra-ket 1 ket 1. Follow, dear students, carefully. That is equal to alpha into bra-ket 1. It is already here. That is 0, 1. Ket 0 already there. 1, 0. Plus beta into bra-ket 1. It is here. That is 0, 1. Ket 1. It is here. That is 0, 1. Okay, now you know how to simplify this. It is nothing but matrix multiplication. Yes, it is equal to alpha into 0 into 1, 0, plus 1 into 0, 0. So this is 0. Correct? Plus beta into 0 into 0, 0, plus 1 into 1, 1. Correct? Yes, sir. That is equal to alpha, sorry, into 0. So this becomes 0. Sorry, this becomes 0. And finally, I have beta. That means bra-ket 1 operating on my psi gives you beta. Sir, what actually you are trying to explain, sir? I am trying to explain the importance or significance or use of bra-ket vector. See, I have a bra-ket vector, that is bra-ket 1. When bra-ket 1 operates on psi, finally what I am getting? I am getting beta. Beta means what? Beta is nothing but probability amplitude of ket 1. Now comes the answer. What is the use of bra-ket vector? When bra-ket vector operates on the state vector, this is called state vector, it gives you probability amplitude. So bra-ket vectors are very much useful to find the probability amplitude. And if you know the probability amplitude, you can find the probability density, because modulus square is probability density. Understood? So what is the use of Bragg vector? Bragg vector gives you amplitude. What is the use of Ket vector? Ket vector gives you the state. That means whether electron in the spin up or in the spin down. That we come to know from Ket vector. How long it will be in the up state, how long it will be in the down state, whether it is only 50% or 100% or 20%, that will come to know from Bragg vector. See dear students, I give you a small assignment. I have operated Bragg on psi Bragg 1. Please try operate Bragg 0 on psi. Please check whether you get alpha or not. 100% you will get alpha. I hope you got the concept of Bragg and Ket. Ket is for representing the state. Bragg, when it operates on the Ket, will definitely give you probability amplitude. Okay, that's all. Now let us proceed further. So far we discussed so many things: Hermitian, complex conjugate, identity, operation of Bragg on the Ket, importance of Bragg, significance of Bragg and Ket, all those things. Now I come with the next topic, that is unitary matrix. What is unitary matrix? I have a matrix, say A. I take its complex conjugate and then I take its transpose. You know what this is actually? Yes sir, we already know it is nothing but Hermitian, sir. Yes, it is Hermitian. So when I multiply these two, if I get number 1, or if I get identity matrix, see in normal course 1 I call as number 1. In matrix form I call it as identity matrix. Okay, that is 1 0 0 1. So then I call this A as unitary matrix. So what is unitary matrix? If the matrix is multiplied with its Hermitian, that is when A multiplied with Hermitian, this is not T, it has to be read as dagger. If it can generate identity, then it is unitary matrix. Or in other words, A dagger is equal to I divided by A. It is nothing but 1 divided by A. It is nothing but A inverse. So if A is really unitary matrix, ನಿಜವಾಗ್ಲೂ unitary matrix ಆಗಿದ್ದರೆ ಅದರ ಇನ್ವರ್ಸ್ Hermitian ಆಗಿರಲೇಬೇಕು, ಅಥವಾ Hermitian of the unitary matrix is equal to inverse of that matrix, ಅಥವಾ when matrix is multiplied with its Hermitian, if the result is identity or I or 1, then the matrix is unitary. 3 definitions ಅನ್ನು ಕೊಟ್ಟಿದ್ದೀನಿ, ಯಾವ್ದು ಬೇಕಾದರೂ ಬರೀರಿ. ಸೊ ಐಡೆಂಟಿಟಿ ಆಗಿ ಬರಬೇಕು, ಕೊನೆಗೆ ಅಂದರೆ 1 ಬರಬೇಕು. ಯಾವಾಗ? when 2 matrix are multiplied. ಆ ಮ್ಯಾಟ್ರಿಕ್ಸ್ಗಳು ಹೆಂಗಿರಬೇಕು? ಒಂದು ಇನ್ನೊಂದರ ಡ್ಯಾಗರ್, ಅಂದರೆ ಇನ್ನೊಂದರ Hermitian. If one matrix is Hermitian of the other matrix, that other matrix is definitely going to be unitary matrix. So I explained you unitary matrix concept. I give you examples. I solve few numericals in my next video. I take up the next concept called inner product. Once I explain all these things like inner product, unitary matrix, and how to find the inner product, then we can comfortably move on to what is called gates, that is quantum gate. Actually, our final intention is to learn quantum computation. Computation means total. I already told you in the beginning, any computer, that is quantum computer or classical computer, rely upon 3 things. Number 1, input. Number 2, process. Number 3, output. That's all. Take something, do something, give something. That's all. Okay. Taking something is in the digit form, binary form. Doing something, that is with the help of gates, and finally giving the output. Okay. So we have so far discussed about the digits, that is qubits. Now how these qubits are processed with the help of gates. So in classical computer we call them as logic gates. Here we call them as quantum gates. So for learning the quantum gate, for knowing the quantum gate, to understand the quantum gate, this matrix knowledge is required. That's why I explained what is called complex conjugate, Hermitian, inverse, transpose, unitary, identity, and also meanwhile I explained what is called Bragg and Ket importance. Well, I will stop this video here. In my next video I will come back with inner product. Okay, I hope you are enjoying. Please subscribe to my channel. Notes link is given here. here, please copy the link or download the material, and also share with your friends this link. Ask your friends to subscribe and also let them get the benefit. Shortly I am going to start with physics of animation, and also I am going to start with acoustics and radiometry for civil branch students. Okay, so please inform your friends in other colleges to watch my videos. Thank you very much.